Thank you, Tom. And hello and welcome, everybody. We are really happy to be here, and we really like to thank the ADC for this amazing event. And thank you all for being here listening to us today. So we are going to talk about some work we did earlier about an AI-powered karaoke system. Quick presentation first. So here is Clément, I am Thomas, and we both work at MWM, a creativity mobile apps editor from Paris in France. We've been building creative mobile apps for more than a decade now, including editing our first app, which is still #1 DJ app on mobile platforms. And we started to work with machine learning and artificial intelligence a few years ago, and one of our latest products is using an AI-powered karaoke system we are going to talk about today. So during this talk, we'll introduce how AI can improve the karaoke experience. At first, we would like to think an original instrumental version instead of not always nice covers. And we would like to be able to find karaoke version for less popular songs, which are difficult to find on karaoke catalogs. And to do this, our objective is to build a complete karaoke track with the instrumental, the vocals, and the synchronized lyrics from any song file, basically. Second, we would like to make karaoke more interactive. And last but not least, we would like to do all this on mobile platforms because that's what we do at MWM, and we think it's the best way to make a service accessible to anybody. And to explain all this, our presentation will be divided in 5 parts. The first 3 parts will cover the karaoke generation system, how to make a karaoke from an audio file. And the last 2 parts will present the app we built from this system. And I now leave it to Clément, who will present to you all the deep learning work he's done on this project.
So, hi, everyone. My name is Clément. I'm the deep learning guy in our duo. So, as Thomas said, I'm going to focus on the first 3 parts of the section that are more into deep learning. So, for karaoke, first you need to remove, or at least lower down the volume of the vocal stem so that you can sing on top of it. So we will need to separate it from the rest of the track so we can control it. Let's dive in. So maybe you might have attended last year's presentation of ADC 2022, where we talked about implementing real-time source separation on mobiles. So for newcomers, I'll do a bit of a refresher, but if you are more interested in the details, you can go and watch our presentation on YouTube. We train our model on a supervised setting, so with 2 stem separation framework, only vocals and instrumental. We have like an in-house data set of 10,000 tracks with pairs of mixtures and vocals. And as for evaluation, we use like the public test set MuseDB, and we assess with quantitative metrics such as the signal-to-noise ratio, as well as we just listen to it so that we see if there are any like artifacts or leaks from the rest of the track. So if it's like good quality for people. So just a quick overview of how it works, the baseline architecture. Oh, sorry. In our framework, we use STFT spectrograms as input. And the basic idea is that we output a magnitude spectrogram mask. We then multiply element-wise this mask to the magnitude spectrogram of the mixture to get the magnitude spectrogram of the stem. We just reuse the phase of the mixture, like as a good approximation of the phase of the stem, and then we just convert it back to the waveform domain. We train with both objectives in the time domain and the time frequency domain. As for the architecture, I won't go much into details. It's basically like a convolutional unit, and we did like a bunch of tweaks and tricks here and there. We ended up with this example I can show you. So here's the mixture. Yes, you recognize that song, and then the vocal. So yes, now we got our vocal track. We can now subtract from the audio the vocals and get the karaoke version. In the same time, we'll also use the same vocal track to transcribe the lyrics with singing voice transcription. So at first, we thought transcribing the lyrics of a song was pretty much similar to like transcribing speech. So we said, let's just pick up any well-known speech transcriber and that will do. However, it didn't turn out that way. It's because singing voice is much more diverse than speech, actually. You have like varying pitch, varying speed, some vocalizations like singing ahs and oohs like that, and it makes the model, the task even more complicated. Plus, in karaoke, you want to have the lyrics synchronized quite perfectly to the vocals, so on top of that, accurate tracking of the timestamps. Moreover, we wanted to transcribe as well multiple languages, so multilingual support would be a huge plus. And as well as you already know, some tracks may have like multiple singers, maybe they sing in different languages, so that's another problem as well. We then tackle them one by one. First, by the end of last year, a new model called Whisper from OpenAI made waves in the ML community. What was special about it, it was like trained on a huge amount of data. Like you can see 700,000 hours of speech from all types of content from the internet. And all this data made it quite suited for real-world speech transcription scenarios. And to some extent, singing. So we tried it out on our singing voice samples. And it turned out that it was already quite robust to singing voice. We then thought it would be a good idea to use this model as a baseline for our experiments. Plus, it already supports like transcription for nearly 100 languages. So we went with this one. Just a quick overview of the machinery. The Whisper is like a deep learning framework based on the simple architecture of the transformer. It's really common in all fields of deep learning. It came out in 2017. Just to do a small explanation of it, you chunk audio into extracts of 30 seconds. Then you process the audio as a spectrogram into the first part of the model, which is an encoder. You get some audio features. And then, in an autoregressive way in the decoder, you want to output the next probable token, given the previous token sequence and the audio features. So tokens are just like bits of words. It can be also by design anything you want, so words and timestamps. And you iterate in autoregressive fashion until you finish your lyrics for every audio chunk. There's nothing more particular than that. So we re-implemented the training pipeline and fine-tuned the Whisper model made open source by OpenAI. And we ended up with actually better performance on our private dataset of lyrics. We got like two commonly used metrics to assess speech transcription quality, CR and WER, who stand for character error rate and word error rate. We focused only on most popular languages, those that are available in our dataset. And we found out that we had like better sentence segmentation, and their lyrics weren't weirdly as before. They remove also spurious punctuation, and mostly we have support for vocalizations. Humming and singing like words that don't carry much meaning, like oohs and ahs. So it's still not perfect, it's still no 0% error, but it's better and it can be like good enough, I guess, for people to sing along. Now that we have made it better, can we make it faster? Yes, actually, like the naive implementation of Whisper has to be run offline on servers for the larger version. With the naive implementation, it takes like 1 minute, for a 4-minute typical track. So we found out about ctranslate2, which is a C++ and Python library for efficient inference and transformer model. With those performance optimization techniques, we already make a 4x in terms of speed, and mostly it reduces GPU and CPU memory costs. So on top of that, we can parallelize audio chunks, so we can make batching, and that makes even more the inference makes it even faster. Also, we have voice activity detection to skip all the silent sections of the track. So we can just get rid of those non-salient parts and focus on the meaningful vocal sections. So in the end, we ended up with a 10x speed up without losing transcription quality. So with batching on our best GPU setup, we have less than 5 seconds for a typical 4-minute track. Okay, so we removed the vocals, we got the script. Now we just need to synchronize the scrolling of the text with the music. I said in the previous slide that Whisper outputs tokens of timestamps. That still holds true, but those timestamps are at the sentence scale. And for a karaoke, you need the synchronization at least to the word level scale, or even the syllable level. So how to deal with lack of accuracy? The idea is to add a small refinement layer in the end as a post-processing phase. For each sentence with timestamps that the transcriber outputs, we refine and get the word-level timestamps for each word in the sentence thanks to forced alignment with another pre-trained speech transcription model called Wave2Vec2. The inference of this model is quite fast. It's negligible compared to the Whisper, so it's not a big deal to add this post-processing layer. So basically, the idea is that we use this Wave2Vec2 model as a black box to get some features out of it. The idea is this. You get an audio chunk, you input it to the Wave2Vec2, and you get for every time frame, let's say 10 milliseconds, you output probabilities for each letter pronounced within this time frame. For example, we have a Wave2Vec2 pre-trained on English. There are 26 letters in English, plus some other special characters like the space one. You can see this in the first figure. We already have the text predicted from Whisper in the previous stage. You put it then in the vertical axis on the second figure. You put then you compute the emission probability matrix. Well, it's not a big detail here, but you have you combine the probabilities from the first figure, and you get this emission probability matrix. You get the yellow diagonal axis, which shows the most probable path for the time range of each letter, and then you just merge back, backtrack the diagonal and merge back all the small letters. Then you get the timestamps for each syllable and then for each word. So if you followed correctly, there's still a hic with this. We had this backtracking and then alignment for English only, because Wave2Vec2 was pre-trained on English only. How to handle all the languages we support already with the transcriber from Whisper. Oh, sorry. Oh, sorry. Okay, was annoying then. Where was I? Okay. So I said the transcriber only handles hundreds of languages, but our aligner only supports one. How to continue to support all the 100 languages? We only had one. We can go for one aligner model for every language, but it would be a bit of a problem in terms of memory costs. Plus, those aligners are not even available for more rare languages. So how do we deal with this? We go for an intermediate representation. We use this solution called IPA, which stands for International Phonetic Alphabet, which is a set of labels used to describe any sound in a given language. So you just give the language, for example, English, you process the letters, and you get some labels from IPA, and this would be the common representation for all the languages. With this, we already have also a pre-trained multilingual Wave2Vec2 with IPA, and this time we can merge every bit together, and we have then the alignment in the IPA realm, and we map back then to the letters we have before. So let's recap all the steps we've covered so far. It's a big figure. We have like first this vocal separation. We just remove the non-salient vocals. We cut, merge, and batch to get all the vocal chunks properly. And then comes the transcription part. We first detect language with whisper. We transcribe all the lyrics and we get the segments with the sentence timestamps. Then, with the phonемization in IPA, we get the IPA segments. In this realm, we do the first alignment. We go back and we get the karaoke script. So here's the summary we've achieved so far in the first 3 sections of the talk.
Okay, thank you, Clément. And so, now we have a ready-to-use karaoke. What can we do with that, and how can we go even further? Because we want to go even further, of course. And for several reasons, we decided to go in the gaming direction. And one of the first things to go when you go with gaming and karaoke is to measure the singer's performance. And there are many ways to measure a singer performance. And at first, we decided to focus on the basics, measuring the pitch accuracy. Ensure the singer is singing in tune. So the idea is the following. On one hand, you have the separated vocal tract from the previous algorithm, and we can run a pitch estimation on that on the server during the karaoke creation process. And on the other hand, we have a singer singing live with a smartphone. We can record the voice, and we can run a real-time pitch estimation on the device, on the voice. And we can compare the two in real time and compute a score in real time on that. So let's get a little bit into the details because the requirements for the two pitch estimators are a bit different. For the reference pitch, we want something as reliable as possible. And computation and latency is not really an issue because we are running on server. So we chose to go with the state-of-the-art Armor F0, which is a deep learning algorithms, which, by the way, is not so long to compute compared to the karaoke generation we've seen before. So this one is perfectly suited for the reference pitch. For the real-time speech, what we want is to provide feedback to the singer in real time. So we need something with low latency. We need to run that on smartphones. So we chose to go with our in-house pitch estimator, which is based on cross-correlation with some refinements. As for the scoring engine, the comparison between the two, as I said, we are building a game. So basically what we did is fine-tuning the time and the pitch tolerance to make the game both enjoyable and challenging for the players who will sing the karaoke. So this seems quite simple, right? But we have one problem. As I said, we're doing mobile apps, and we want them to be as user-friendly as possible. And especially, we want the users to be able to run our apps without nothing more than their smartphones. So you may see one problem coming, and that is the feedback loop. Because we have a smartphone with a loudspeaker screaming music out loud because you don't want to do quiet karaoke, right? This is something fun, you want some loud noise. And there is a microphone right next to it, which is recording both your voice as the singer and the music. And we want to isolate the voice. So here is a quick example to give you an idea. So let's take some music, I guess everybody knows.
There's not a soul out there. Don't want to hear my prayer.
Okay, now we play this music on a smartphone, and we ask a singer to hold the smartphone in their hand, sing along, and we record what the microphone captures. And this is what we obtain.
There's not a soul out there. Don't want to hear my prayer.
As you can hear, the music is a bit distorted, and the singer is not very loud compared to the music. And what we want is to isolate the singer in order to run a pitch estimation on the voice. And for this, what we need is called an echo cancellation. And we did an echo cancellation, which is adapted for singing voices, which is robust to really low SNRs, because the voice is low compared to the music, which is robust to non-linearities, because we have loudspeakers, tiny loudspeakers screaming music with non-linearities, which is compatible with mobile devices, and with a quality good enough to run a pitch estimation. We don't know the perfect voice extraction like in the first parts, we just need to run a pitch estimation. After some benchmarks, we selected a deep learning method called DTLN, which works quite fine, but not exactly where we want to go, because it's more adapted to speech than singing voices. But yet, it was the most promising we found. And this is what you obtain if you send the two sounds you heard before through the DTLN. And as you can hear, we have two problems. Well, the voice is a bit distorted, but as I said, it's not really an issue for now because we just want to run a pitch estimation. But the sustained vowel at the end is completely cut off, and that's a real big issue. And that was the biggest problem with DTLN is that high-pitched voices and sustained notes were completely cancelled by the algorithm. So we need to return that. And to do this, to do this, we used a microphone loudspeaker system simulator, and we retrained the model on augmented data. And at the end, we obtained an echo canceller, which is much more efficient. Still not perfect to isolate the voice, but let's hear what we obtain with the exact same two sounds, but with our retrained model. Okay, it's not perfect. It's not voice extraction that we heard before, but we can run a pitch estimation on that, and we get these sustained notes back. This is what we wanted. So finally, with that, we build a core ML implementation to run this on iOS device, and hurrah, we solved yet another problem. So to summarize, right now we have a karaoke generation system with the source separation and the lyrics transcription. We also have a reliable system to monitor the singer's voice through the smartphone microphone, even where they are listening to really loud music. All the ingredients are here, and we are ready to make a mobile app. For the final touches, we added a pitch and tempo control so that the user can adapt the music to their voice and skills. Again, user-friendliness. We added also a visual pitch guide, which we built with pitch segmentation algorithms, and a control of the original voice volume to use it at the vocal guide. And thanks to the echo cancellation, even if the voice volume is here, the original voice is here, it doesn't interfere with the singer's voice quality measurements, thanks to our echo cancellation. And I think it's time for a little demo. So I'm not going to sing live because you really don't want to hear that. So I pre-recorded a demo with my colleague Adrien, you might have seen last year in the source separation talk, and who sings much better than me. And here is you sing on iOS. At first, let's create a karaoke. You can pick a song from Apple Music or any audio file from your device. And we'll continue with our beloved Chandelier from Sia. So all the separation, all the magic happens on the server. After a short while, you get to karaoke and you are ready to have fun. So in the first part, Adrien is actually not singing. And you will see that even though the music is here and is loud, all the notes are failing.
Party girls, don't get hurt, can't feel anything. And when I learn, I push it down.
Without the vocal guide.
It's some call, phone's blowing up.
Now let's start again with Adrien singing, and as he's a wonderful singer.
Party girls, don't get hurt, can't feel anything. When will I learn? I push it down, I push it down. I'm the one for a good time call, phone's blowing up, ringing my doorbell. I feel the love, feel the love.
And now for the fun parts, let's ask Adrien to sing out of tune to see how it works.
1, 2, 3, 1, 2, 3, 3. 1, 2, 3, 1, 2, 3, drink. 1, 2, 3, 1, 2, 3.
And you can see that all the notes are failing. He really hated me for that. So yeah, you can see that all the notes are failing, even though the vocal guide is on, again, thanks to our echo cancellation. And that awful off-key singing concludes our very brief using demo. You can come out a booth if you want a more detailed presentation. So to conclude, we presented our work on transcription and source separation, transcription and echo cancellation, which enabled us to build a fully featured karaoke system. And of course, this is just a beginning. There is much, much more we can do with that. We can improve the transcription. We can improve the speed of the backend service. The Karaoke generation is still a bit long for the moment. Like Clément said, we can take multiple singers into account. For now, if there is multiple singers in the original track or in the live performance, we don't take that into account, and that really messes up the system a bit. And we can make our echo cancellation algorithm more efficient and compatible with all speaker setups, as right now we only validated it with a smartphone, loudspeaker, smartphone, and microphone, and we haven't tested it and validated it with other speaker setup like Bluetooth, loudspeaker, or anything. And I hope you enjoyed the talk. Thank you again for being here with us today, and we will be happy to answer your questions.
Thanks, really fun talk. Thank you so much for sharing. I know you touched on the ML ops side. I was wondering if there's any insights or anything you guys could share about things you learned or stuff that worked well for you or didn't work well for you or anything like that.
Mm-hmm.
I'll let you answer.
Okay. Yeah, because I'm more on the ML ops side. Like on what section do you want to focus on, like source separation, lyrics transcription, maybe?
Like just keeping like costs down, or like, are you running it on-prem? Are you using cloud? Are you using like third parties for like what's the stack that you guys have what stacks have you guys figured out that work well or don't work well?
Well, it's we work on the cloud. We have like inference servers on the cloud, and we have like optimized our models first for source separation thanks to our last year's work. And we wanted to run, like, for example, a parallelization between some tasks. Every time you can think of parallelization, just let's go, and you can like load the models on the same GPUs, for instance, because like, for instance, we have pitch detection, which run on the same GPU as force alignment, for instance, and this makes it like optimized. Otherwise, you would not use like this free memory on the GPU. So would you just combine somehow like some inferences that can make up, like, for instance, if you have like 16 gigabyte GPU, you have like a 9.1 and a 5.1, it would be better than to load more. So I don't like teach you something great, but it's like the first one. As for the lyrics transcription, it was quite seeking through all the different like inference systems. And we found out that sometimes when you go for a floating point 32 or 16, you really need to check your configuration with like your GPUs. For instance, A100 or V100 and stuff like that. It can be quite surprising. Always do your tests because sometimes you might end up with something slower than you wanted to, or you expected. And I can't think of any.
Yeah. There is also one point which is quite basic, but we often miss it. Well, we have a caching system, and so if two users upload the same music, we don't run the algorithm twice and the transcription and everything twice.
Do you do that on like a cache on like the hash of the binary that's uploaded?
It's a little bit more refined than that. We have duplicated audio algorithms.
Oh, okay. So you'll do it like a diff of the samples, basically. Oh, okay.
Well, not exactly, but yeah.
Yeah. Sure. Oh, that's really smart. That's really cool. Brilliant. I just had one cheeky question about you do source separation and then you're getting the F-zeros. What do you do about harmonies when it comes to F-zeros? Is that a problem you guys have faced?
That's what I said at the end. Multiple singers are not taken into account for now. Okay. So this is not really efficient, basically. Okay. And it messes up with the system a bit. And this is one thing we need to do. The app is not fully finished. The service is not fully finished, I would say. It's available on stores, but we didn't put the market yet on that. So there are lots of refinements to do, and this is an important one.
Thank you.
Hi, thank you for the talk. This might be a dumb question. I don't remember my signals and systems class that well. I've used spectrograms for like transcription problems, but I don't know much about like going back from like your spectrogram to audio. Is there any information loss like when you're going back the other direction? Yeah, besides the mask that you wanted to get rid of, yeah.
Well, you have like the magnitude mask. You multiply with the magnitude spectrogram of the mixture. So you get the magnitude spectrogram that you want, and you reuse the phase of the mixture. So you have your phase. So as long as you have like your magnitude and your phase, you have your whole spectrogram. And you just do inverse STFT, so you get back to raw waveform.
This is kind of a trick, but it works basically.
Yes, the fact that you use like the phase of the mixture as an approximation is kind of a trick. Yes.
Right, okay.
That was another question there. Yeah.
Mm-hmm.
Yes, I just had a question. Are you able to run any of the inference on the device itself? Are you using Core ML or things like that?
Only for this app, Core ML is used only for the echo cancellation. The source separation, actually we could. We have another app called Stems where we run the source separation real time in the device. But for several reasons, we chose to go cloud because anyway, the lyrics transcription is too heavy. So we had to go to the cloud for some of the tasks. So the source separation in that case is done on the cloud, but the echo cancellation is real time.
So when someone's playing and singing, that analysis that's knocking off the notes and so on, that is doing a round route to the cloud the whole time. Okay.
No, the analysis, the echo cancellation is real time on device. It's
Okay.
not through the cloud.
And the pitch detection and the
Yeah, also on device.
and that's on device.
Yeah.
Okay.
The
And then
only thing is
timing?
the karaoke creation with source separation and lyrics transcription is on cloud. All the rest is on
Everything
device.
is on device. Okay, fantastic. Thank you.
Welcome.
Well, I have a question. There is a fantastic array of really cutting edge tools released in the last couple of years. Is there anything that you know of on the horizon or like a project underway that will change the way that you do anything now? Just in the whole pipeline.
Good one.
I didn't really understand the question.
Say there's a new release of new technology from OpenAI. Do you know of anything on the horizon where you're thinking, like, you're really waiting for it, you're really exciting for it?
I don't think, we don't have direct contact with the OpenAI guys, unfortunately.
It's already hard to keep up with the latest releases, actually, so yes.
Yeah, no, basically with these big actors, we try to keep up and stay aware of what they release. And when they are releasing interesting technologies, we try to see how we can use it. But no, I couldn't say what will be OpenAI's next major steps in the future. I have no idea. So we'll try to keep up for sure. And if they can help us, tackle some of the other issues here, we definitely use that. But we also are doing much of the work in-house. So we also have some new technologies every year. So.
Thanks for the talk. I have a question regarding lyrics alignment. We all know that when actual music performance, there are a lot of weird things that could happen to singing voice. People can sing any irregular stuff, and which is also true to the reference recording, the reference track you're using. So what happens if your the lyrics given differs from what's actually being sung? For example, there is an awkwardly long silence that's not transcribed. So do you find these edge cases challenging, or do you have any threat strategy to deal with these during alignment?
We found out about those edge cases, like when lyrics transcription fails a bit, when you have also like the sentence timestamps initially given by Whisper, which fails, you have like this first alignment that would like kind of eventually give a huge gap of silence, especially in the beginning. So our tricks would be to re-loop, like somehow, voice activity detection then, so that we can cut out and rephrase it in a new way. So that's for the timestamps. As for alignment, if the words are already failed, this is like the result would be like a failure. So yeah, it would be a bit bad. So sometimes it happens, yes.
But are you using like existing lyrics that's already available, using it like a reference to guide the transcription?
So we train our models at first on a singing voice data set, yes, but then it's just like data-driven. So we ended up with it. We just output the lyrics, and that's it. Yes.
Oh, that's quite amazing because it seems like you have pretty good accuracy. Thank you.
Hi. I have a question regarding the echo cancellation. Which devices are required to run it? And did you actually release the model?
So we didn't release the model openly. And for the moment, the model, we implemented a core ML implementation of the model, so it runs on iOS devices, any iOS devices. We don't have an implementation for Android or web because, yeah, I didn't say it, but the application is also available on the web. So on the web and on Android, you don't have the real-time scoring for the moment. It's on the iOS device because we only implemented a caramel version of the model. But yeah, we should be able to do that in the future. But that's still a work we have to do.
There are a few questions online as well, actually. Someone asked, will there be an Android version of the app?
Yeah, so there is an Android version. The only difference is that the scoring engine is not available, as I said, due to the echo cancellation, which is not yet available on Android. There is an Android version and there is a web version on the app.
Another question was, what is the latency of the echo cancellation system? And is it running locally on a machine?
Other figures in my head. It's quite small because you have real-time feedback. I guess it's under 100 milliseconds. I'm not sure of the exact number, but it's quite low. It's low enough to run some visual real-time feedback.
And someone else asked what the brainstorming ideation phase of your team is like and how you guys came towards actually coming up with the idea of the Karaoke app.
So we had the source separation. We released the source separation app last year, and Karaoke was actually a long-time project at AWM. We had a first Karaoke app a long time ago with some content we negotiated with in terms of copyrights. And we saw that source separation was a good opportunity to make an app where users can build their own karaoke and, like I said in the introduction, an app where they can use the original instrumental. And we have some people loving karaoke at the NWM, and we all know the problem of you go for a karaoke version on YouTube and you find a really cheap piano version of the instrumental, and it's quite frustrating. So the source separation gave us the opportunity to run a karaoke with the original instrumental. And after that, we knew that we had kind of issues, but we love challenges. So we started to tackle all the issues one by one. And as karaoke was like a non-time project, we tackled all the issues like we do always.
All right, I think that is us out of time. Please give the chaps from MDM a really warm thank you.